Okay, so continuing on from the last video where we found the three eigenvalues, lambda 3, lambda equals 1, lambda equals minus 4, we're now going to continue and find the corresponding eigenvectors. So we're going to be using this formula here, a minus lambda I x equals 0, and here's just a reminder of the matrix A. So the first thing we're going to do is we're going to use our first eigenvalue, 3. So we have a minus lambda I times x equals 0. And if we do that subtraction, all we really do is subtract 3 from the leading diagonal. And it gives us this new equation here. Now if we look at row 3, we can see that it tells us nothing. It tells us that 0 lots of x1 plus 0 x2 plus 0 x3 equals 0. So there's nothing to be gained from looking at row 1. So we need to concentrate on row 1 and row 2. If we look at row 1, we see that we have minus x1 minus 3x2 equals to 0, which will tidy up to give minus a third x1 equals x2. However, let's have a quick look at row 2. If we look at row 2, we see that we'd end up with a quarter x1 equals x2. And the thing to spot here is that these two are not equal. So how could we have spotted that? Well, it's a little bit easier in this case because this final column here, column 3, they're all 0. So we're only really looking at the minus 1, the minus 3, and then the 2 and the minus 8. We can see they don't have the same relationship. So minus 1 and minus 3, well, they're out by a factor of 3. That's not the case with the 2 and the minus 8. So what it really means is that this can only be true if x1 and x2 are 0. Then of course a quarter of 0 will equal 0, and minus a third of 0 will indeed equal 0. So we have to watch out for these things. So from there we can write up our eigenvector associated with that eigenvalue. So we know that x1 is 0, we know that x2 is 0, and what about x3? Well, we don't know anything about x3. What did we do in a nicer question when we had to come to the eigenvector section? We said let the first non-zero value, typically that was an x1, equal 1. Well, x3 is our first non-zero value, so we let that equal 1. So our corresponding eigenvector is just 0, 0, 1. Okay, let's look at the next eigenvalue, lambda 2 equals 1. So in this case, once again, we just subtract 1 from the leading diagonal, and that's already been done in this case. So here's my leading diagonal with the 1 subtracted already. So I can see from row 3 that 2 lots of x3 will equal 0, so therefore x3 equals 0. Now, if I look at row 1 and row 2, I can see that the elements within them have the same relationship. So in row 1, I had a 1 and a minus 3, and then in row 2 I have a 2 and a minus 6. So in this case it wouldn't make any difference whether we picked row 1 or row 2. So if we go with row 1, we see that x1 minus 3x2 is 0, and from there we can tidy that up and we get 1/3 x1 equals x2. So we write out our second eigenvector. We let the first non-zero term be 1, so we have a 1 for x1, and then x2 is a third of that, and then 0 for x3. And then again, typically multiply out to get rid of the fraction, so we times by 3, and we get our corresponding eigenvector 3, 1, 0. In the last case, we have lambda 3 equal to minus 4, and once again, we're going to subtract lambda from that leading diagonal. So in this case, of course, it's minus 4, so we add 4. And that's been done in this matrix. So once again we can see from row 3 that 7 lots of x3 would equal 0, so x3 must equal 0. If we have a quick look at row 1 and row 2, we can see they share the same relationship. Let's look a bit scruffy there, it's meant to be a 6. So we have 6 and minus 3 and 2 and minus 1. Therefore we could pick either row 1 or row 2. If we go with row 1, we have 6 x1 minus 3x2 equals 0, and from there we can see that 2x1 equals x2. So we'll let x1 be 1, x2 is twice the size, and of course x3 is 0. So there we have the final eigenvector of 1, 2 and 0.